General relativity does not say there is no gravity. General relativity, as you say, the second part of the statement, that gravity is a manifestation of curved nature of space-time. And so again, everything that is explained by Newtonian gravity is explained by general relativity as a special case. Interestingly, over the last 100 years, it took a long time to understand, to obtain observational evidence of general relativity. But now the technology has finally caught up, and there are many confirmations of Einstein's idea of this curved space and time, the idea that gravity is encoded in the very geometry of space and time. And I mean, one of the sort of obvious ideas that you and I feel or use all the time has to do with the cell phone, right? We use it all the time. I wrote to Feynman saying that, well, I mean, this answer seems to be wrong because of this reason. And then Feynman actually replied and saying that, yes, the book was wrong, you're right. And I was very, encouraged by that. But more than that, in practical terms, it helped me enormously because this letter from Feynman was a big boom. So that because then I got admitted to the PhD program in University of Texas at Austin. So he invited these three young, bright people, very young people at that time, to come to Chicago for summer and lecture him. And these three people came and gave lectures on various, forefront topics of general relativity. And Chandra, as a student, went to all those lectures and took detailed notes.
So, hello दोस्तों, स्वागत है आप लोगों का एक बार फिर से रोजेंडर पर। और बहुत समय बाद ये चीज़ कह के बहुत ज़्यादा मज़ा आ रहा है। लास्ट टाइम हम लोग मिले थे FAQ के जो होस्ट हैं प्रतीक सेठी, उनसे मिलने के बाद अब आप लोगों को एकदम डिफरेंट कॉन्ट्रास्ट पे मैं लेके जाना चाहता हूँ। एंड आप लोगों से किसी ऐसे शख्स को मिलवाना चाहता हूँ जिनसे मिलने की काफ़ी लोगों की तमन्ना है और उनसे वार्तालाप करने की, उनसे बात करने की, जस्ट टू हैव अ कॉन्वर्सेशन विद हिम। देयर आर अ लॉट ऑफ पीपल हु वांट टू डू दैट, एंड जिनका भी कॉस्मोलॉजी में, एस्ट्रोनॉमी में इंटरेस्ट है, उन लोगों को ये चीज़ बिल्कुल देखनी चाहिए और उनको बिल्कुल मिस नहीं करनी चाहिए। So today we have on Rozender Talks with us Dr. Abhay Ashtekar. So welcome you, sir, on the second season and second episode of Rozender Talks. So first, let me ask you, how are you?
Okay.
And how things are going? Like you have been there, and it's morning time there, and I'm recording this in evening. So let me start with the part one of the interview, which is a little bit about the research part. And you have been doing cosmology and general theory of relativity as your research part. So please tell us something about your research in both the fields, in general relativity and how it went in cosmology, and the research on cosmology.
Right. So general relativity is Einstein's theory of gravity that generalizes Newtonian theory of gravity, which I think most people in high school know. The main problem was that the basic principles on which Newtonian gravity rests are in conflict with the principles of special relativity. In special relativity, space and time fuse into a four-dimensional continuum. Whereas in Newtonian theory, you have a notion of absolute time. So in special relativity, the passage of time, the rate of ticking of clocks, depends on the speed or the velocity of the observer, depends on the rest frame of the observer. Whereas in Newtonian physics, time is just absolute. It is the same for all observers. So there was a big conflict, and Einstein had discovered special relativity in 2005, and it was clear that really removed a lot of puzzles that people had about the theory of electricity and magnetism, so-called Maxwell theory. But then Einstein realized 3 years later, in 2008, that this special relativity and Newtonian gravity are in conflict with one another, And therefore, he started thinking about how to resolve this conflict. Namely, if I now, for example, take this object up here, and if I move it, then according to Newton, the gravitational field changes, and you sitting in India would perceive that change of gravitational field instantaneously. Whereas in special relativity, really signals can propagate at most with speed of light, so there will be some delay. So there is a tension between the notions of space and time of special relativity and those of Newtonian theory of gravity. And so Einstein was then worked very, very hard for 8 years and came up with general theory of relativity, which unifies Newton's theory of gravity with special relativity. So both Newton's theory of gravity and special relativity are special cases, limiting cases of general theory of relativity. General theory of relativity is a grand theory from which these two theories emerge as approximations in suitable limits. So what happens in general relativity is that space and time not only fuse together to form a four-dimensional continuum, but in fact this continuum is not flat. Usually we think of, you just look around you and you think of space as being flat and time just marching along, like the screen that you see in front of you, it's just flat, two-dimensional flat. So we think of space being three-dimensional flat continuum. And in general relativity, this is not the case. It's actually bent. And the bending of space and time encodes the gravitational field. So strictly speaking, in general relativity, there is no such thing as gravitational force. What Newton called gravitational force is a manifestation of the curved nature of space and time. So the sun, for example, bends space and time around it, and so it is bent like that, and the earth is trying to move in that bent space and time. And when it is moving in that bent in space and time, from Newtonian perspective, it actually looks like it is on an elliptic orbit. But in general relativity, it is really trying to follow the straightest possible path, but in the curved geometry of space and time. So this fusion is really very profound. It was recognized as the most sublime creation of human mind. And interestingly, over the last 100 years, it took a long time to understand, to obtain observational evidence of general relativity. But now the technology has finally caught up, and there are many, 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 many confirmations of Einstein's idea of this curved space and time, the idea that gravity is encoded in the very geometry of space and time. And I mean, one of the sort of obvious ideas that you and I feel or use all the time has to do with the cell phone, right? We use it all the time. Now, in the cell phone, we got maps, and that uses global positioning satellites, but the satellites are far away from Earth, and they're moving, and therefore clocks that tick in satellites and clocks that tick on Earth, they don't tick at the same rate. First of all, because of motion, and because, so to say, the gravity is weaker there than on Earth up here. So both these effects combine, and this is not trivial in the sense that one might think that this bending of space and time and all that is all this abstract nonsense, abstract notions. Maybe it's okay for people like me who do science and so on, but what does it matter in everyday life? And it does matter in everyday life, because it is literally true that if you switch off these effects of special and general relativity of ticking of clocks at different rates, you would lose accuracy, and pilots would not be able to land a plane on a runway within 2 minutes, just 2 minutes. The accuracy. So these effects are interestingly are incredibly important even in our everyday life. But they are much more important if you want to understand the cosmos, the universe as a whole, and so on, which cannot be explained just using Newtonian theory of gravity. We do need the general theory of relativity.
Just a question struck in my mind, and I want to ask that. There was a video circulating in the internet. Like I saw that video, which shows that sun is like all the planets are moving around the sun, and while they were moving, it was shown that sun was bending the space and time. But simultaneously, it has been showed that sun is also moving towards the galaxy. So it was shown like the all the planets are moving in spiral motion with the sun in that direction, where sun is moving forward in the galaxy. So how that thing is perceived in general relativity? Just a question that struck in my mind. And before you answer, sir, I would like to just apply a few visual effects on my background so that the interview gets more interesting.
Okay. So the statement basically is that yes, I mean it's all completely within general relativity. What you're saying about sun moving and planets moving is not any different from the fact that moon is going around the earth, but earth itself is moving around sun. So moon is really going in some helical orbit, some spiral orbit. I mean that's and now the statement is the sun itself is moving, and therefore the earth is also moving in a helical orbit because sun is moving. And in the rest frame of sun, if you just look at sun as being static, then earth is going in an elliptic orbit. But on the other hand, since sun is moving, it's going in a spiral orbit. So those things just follow from equations of general relativity. And the statement is that if you take into account curvature of not only of the sun but also of the galactic, the fact that the sun is moving because take into account and the entire galaxy, which accounts for the motion of sun in the galaxy, if you like, then the space-time curvature is such that, in fact, the planets are also trying to move in the straightest possible path in this curved geometry, and then that would appear like this helical orbit or spiral orbit that you talked about.
Just one more question about this topic, and I'll move forward. When it is said that the gravity is there, and the general theory of relativity says that there is no gravity, there is just a manifestation of gravity. So how to in that case, how to explain the tides in the oceans that has been occurring? So how to explain that?
General relativity does not say there is no gravity. General relativity, as you say, the second part of the statement, that gravity is a manifestation of curved nature of space-time. And so again, everything that is explained by Newtonian gravity is explained by general relativity as a special case. So the tides are also explained. I mean, again, it's really the water is moving, is attracted. Newton would say it's attracted towards the moon, and general relativity would say that, well, the moon is perturbing the curvature of space and time and around Earth, and that is then affecting water. So everything that can be explained by Newtonian theory of gravity is accounted for general relativity in a special limit, in the sense that it's a good approximation so long as gravity is not too strong, but not near a black hole, for example, and so long as the speeds are not comparable to speed of light. The moon is not moving anywhere near the speed of light, and therefore the Newtonian theory works very well. If moon were moving near the speed of light, the Newtonian theory would not work. There would be, so to say, big corrections to what the tidal table, if you like. But that would be given by general relativity. So general relativity is just a much more accurate theory.
So in 1905, when Einstein wrote his first paper on special theory of relativity, and then later the general theory of relativity came, and in 1920s, two scientists of India, Meghnad Saha and Sir S.N. Bose, both translated the German paper into English. So that's the thing happened, and that is a core history of general relativity. So I just want to ask how Dr. Abhay Ashtekar got into the general relativity. What was your story coming into the core general relativity part, and how you became the cosmologist and the physicist?
Yeah, so basically when I was in high school, by chance came across these books of George Gamow, which are popular books. So you said that students follow your channel, so I would urge students really very much to look at these popular books, not only just the um, just what one sees on YouTube and so on. The reason is because there is a lot of confusion on YouTube. Sometimes things are not really accurate, whereas these well-established classics, they have been, vetted for accuracy. So, for example, for another book that I recommend highly to beginning students would be a book called The Cosmic Code, and this was. I'll think of the author just in a minute. And this book, Cosmic Code, gives a very good introduction to general relativity and also quantum mechanics. So this is a good reference. Okay, so I came across this Gabow's books, and there in particular there was a book on early universe cosmology. So that really interested me. I started thinking about it. Of course, I did not have a mathematical background at all, but nonetheless, then when I was in a small city called Kolhapur for my high school and for my first 2 years of college. This is in Maharashtra, southern Maharashtra. And then for the last 2 years of college, I decided to go to Mumbai, and I went to the Institute of Science, which at that time was considered as the more scientifically, more research-oriented place to do undergraduate BSc. And at that time, I luckily able to contact people in the Tata Institute of Fundamental Research. They were very kind. The senior professors there, Professor Udgaonkar and Professor S.M. Chithre, B.M. Udgaonkar and S.M. Chithre. And they hosted a bunch of us, I don't know, about 6-7 of our undergraduate students from various colleges in Bombay once a week. And that is where I kind of was able to, it was inspiring for me to see how people actually do research and so on. And then I wrote a little article. It was kind of a very, very simple-minded, but I was trying to say that, well, supposing Newton's gravitational constant was not a constant, but it was changing in time. Much later, I found out that Dirac himself had such an idea. But then the statement was that if it was changing in time, how would these simple calculations or simple predictions or observations that Gamow had made about the early universe would change? So I worked that out. I presented it to Professor S.M. Chithre, and even though it was very, very simple-minded, he thought it was quite nice that somebody starts thinking about these things already at an undergraduate level and so on and so forth. And then it turned out that as a result of those lectures and these meetings in the Tata Institute, we also, at that time, the so-called Feynman lectures in physics had come out, and they were very hot, and they were very popular. People were studying them. So I studied them, and then I found that there was a very tiny mistake somewhere in the book. So I had the chutzpah, I had the courage to write to Feynman saying that, well, I mean, it was interesting because the point was that, when I did that problem the first time around, that problem in the book, I got the same answer as was given in the book. But then I realized that, no, I had made a mistake. And when I found the subtlety in the mistake and I corrected it, I got a different answer. And so I wrote to Feynman saying that, well, I mean, this answer seems to be wrong because of this reason. And then Feynman actually replied and saying that, yes, the book was wrong, you're right. And I was very, very, encouraged by that. But more than that, in practical terms, it helped me enormously because this letter from Feynman was a big boom. So that because then I got admitted to the PhD program in University of Texas at Austin. Already just after BSc, normally people were admitted only after MSc, just because in United States and Europe, people get their bachelor's degree when they're 22. In India, they get it when they're 20. And so there is 2 years of less of education, so on and so forth. But I got admitted there. Now, I went to Austin precisely because it was the strongest center worldwide for general relativity. And I found that out just by visiting the USIS. In those days, we didn't have internet. There was no way to look this up at all. So I went to USIS in Mumbai, United States Information Service. And there they used to get these little booklets telling graduate programs in all science, in all areas. And so in physics, and that's how I found out that Austin was the strongest place for doing general relativity and gravitation. And as I said, I'd already begun interest in relativity and gravitation because of these little calculations I was doing and reading that I had done. And so that is how I went to Austin. And I also have a tendency of not being in a crowded area. I mean, I don't thrive when everybody is trying to, competing against each other for the latest little, or not little, but latest step, latest moving forward. I like to be more, have my time to think about things more deeply and not being in a rush to think about them. And at that time, general relativity was more quiet field. Now it has become much more hot because of gravitational waves and such things, and cosmology discoveries. And so I thought that this was a place where one could do some careful, deep thinking and make some contributions that might be lasting. So that's why I decided to go to general relativity rather than particle physics, which at that time was much more quote-unquote hot. I mean, the two are related. They're not completely independent, but the emphasis, there's also a big difference between the two fields. So that's how I started in general relativity and cosmology.
So the time you started general relativity, there was not a boom of general relativity, and there were no such people in general relativity who were like, it wasn't popular between the physicists at that time, but condensed matter physics and particle physics was more popular. And even there were questions about, does black hole really exist or not? So at that time, how did you started your research, and how it came along to the point that you extended the research of the general relativity, whatever was there in general relativity, you extended that research?
So, as I mentioned before, that I started working in Austin. And Austin, there was a really stellar cast of people. I mean, maybe your audience doesn't know these names, but these were the real leaders in general relativity, which were all very much together in Austin. I mean, Roy Kerr, who discovered the Kerr solution, which describes the black holes. Then there was Jürgen Ehlers, who started the Albert Einstein Institute, was founding director of the Albert Einstein Institute later in Germany. And then, and I mean, there's a whole host of such people. Ray Sachs was was prominent both in gravitational wave research and in cosmology, and so on. So, and there was a very young person who had just joined, who had just gotten the faculty position, but he was so good that they offered him a tenure faculty position right away, which was unheard of. And that was about Robert Garrosh. And I was very, very taken up by his spirit of doing physics and by his energy and by his clarity of thought, particularly clarity of thought, the way of speaking and such things. And so I started working with him. And then he moved to Chicago a year later. So I moved to Chicago with him. And in Chicago, then I met Professor Chandrashekhar. We called him Chandra. He asked us to call him Chandra. And I think that I was really very deeply influenced by these three people. The first is Robert Garrosh, who was my PhD advisor. And from Robert Garrosh, as I often like to say, I learned, so to say, how to think sharply, clearly, and in some ways from scratch. So we called it Bob. And so Bob used to sometimes take us for a pizza dinners. He lived far away from the university. And so once a week, we had dinner near the university before going home. And then he would bring a stack of new papers. In those days, there was no internet, so there was a stack of new papers. And he would tell us, you'll read the title and the abstract of the paper and ask us to try to figure out how it was done. So we had to think from scratch. I mean, we don't read the paper. We were at the same level as the author, if you like. Of course, we couldn't, in this dinner, we could not really do everything in detail, but could we understand the key idea? Could we come up with a key approach as to how the calculation started, what the logic was, and so on and so forth?
The real brainstorming sessions were
it's
there
a very
in the pizza party.
Session. Pizza dinner. Yeah, it was not a big party. It was just a pizza. Like, there were only 4 people or 5 or 5 people at the most, including Bob. And so that was very, very that is what I learned from him, of thinking from scratch. I mean, in other words, not so much by reading and so on, but coming to conclusions, having a solid core of understanding and knowledge from which you can then derive things. Of course, it's much slower than reading the paper, and there is a balance that has to be struck. And I have gone a little bit too much to the thinking from scratch side.
Was he the same one who left the car to discuss
Yeah.
paper with?
Yeah, exactly. So once we were discussing something that day in Austin. This was before we moved to Chicago. I just started thinking about it, and so we had discussed some point, and we were puzzled about something. And then in the meanwhile, he figured it out, and I was walking home on the main university drive, and his wife was driving the car. So he asked us to stop the car, and he jumped out for a minute to tell me how to do it. I mean, such simplicity and such energy and such directness, and it's like treating everybody. We are all equal. There's all this problem, and we are all equal, trying to fight that problem. And there was no kind of no rank, no politics, I mean, it was just pure joy, pure science, and that really is what attracted me to his style of doing. And I learned enormously from Bob. And then from Chandra. I mean, Chandra, it's not so much technical things, because Chandra's way of doing science was, and technically, was different from mine, in the sense that he was a master of differential equations and sort of the classical mathematics, and I'm not, I never was. I more like to understand structure, so it is mostly the later half of 20th century mathematics, structures and various other the branches that came up that then laid foundations of both general relativity, namely differential geometry, and quantum mechanics, namely Hilbert spaces and analysis. So I was in that way. I was a different kind of mathematics. Of course, we did have a lot of scientific discussions, and Chandra was a towering figure, right? I mean, he was like a god for me, right? I mean, and the fact that he could actually, discuss in his office what he was doing, and he came to all seminars, and from him I learned something much deeper, and that is really, in some sense, the spirit of science. I mean, ethics of science, the integrity of science, values that you put when you are a scientist. And it is not sort of the outward recognition, but the inner urge to understand things very, very deeply. And I learned from these things, which are much more abstract. I mean, this you learn only by osmosis, by being with these people. It's not some some principles that you can write down that can be followed. And then Chandra actually highly recommended me to go to Roger Penrose in Oxford as a postdoc. I was fortunate enough, partly because I was with this very good group of people in Chicago, to get several postdoc offers. And Chandra said that, well, I should just go to Oxford. So I went to Oxford, and that I met Roger. And Roger is the third person of these three people I told you really who influenced me very deeply. With Roger, I learned something else. I saw him in action. The year I was in, the first year actually, I was in postdoc. He discovered what is known as nonlinear graviton. The details are not important, but it brings together two different areas of mathematics, and to solve a problem in physics. I mean, that was really very interesting. So I could see him getting there. It's almost like watching Einstein coming to general relativity. I mean, not on the same scale, but still, it was a bit like that. And it was, so basically, I could see him thinking in the dark, like as I like to say, groping in the dark to find shapes. But then he recognized those shapes before they came to light, before light shone and said that these are the shapes, so to say. So how to recognize these shapes before light shines on them? It's groping in the dark, this abstraction, this again is this, what is common in all three is really passion for science, but it is manifested in it's an art which is exercised in very, very three different ways. And it's almost like a ballet in which you learn very different things. And from Roger, I learned this mostly. I hope I try to learn. I mean, by osmosis, I picked up this idea about trying to grope in the dark and find structures. And so these three are what really influenced me deeply. to do my research in general relativity.
Just I don't know how appropriate this question will be, but I want to ask, like, in today, when someone wants to do research on cosmology, do relativity. One of my friend is doing his masters and was researching on relativity. There are a lot of graphs and there are a lot of computer codes that are shown on, like, their Insta feeds and their social media. So what was that time when you started researching on the theory? Why and how you people used to do your research at that time, and that change in time, how did you adapted that, like, the ages of computers, and now everything is done on computer, and you people used to what was your idea, and what was your, मैं बस ये कहना चाहता हूँ कि किस तरह से आप लोग रिसर्च करते थे?
Right. So no, you are completely right. It is completely transformed, particularly in areas of fundamental physics like general relativity and cosmology. And also, I should say, I forgot to say this, that already for my PhD with Robert Garrosh, I started thinking about unification of quantum mechanics and general relativity. So half of my work has been in quantum gravity, and half of it has been in general relativity and cosmology, classical parts of general, in which quantum mechanics plays minimum role. So you're quite right that the field has evolved enormously. And in our days, it was all pencil and paper, right? I mean, we wrote pencil and paper. And even the very first paper I wrote, not very first paper, the first paper we started, loop quantum gravity program, which is in which I introduced this variables to describe general relativity, which have been since named after me. That paper was handwritten, and Carlo Rovelli found a Xerox copy of this handwritten paper. I don't have the original one, but Carlo Rovelli found a handwritten copy and sent it to me. So you see how even the paper was handwritten, even the paper was not typed, and then you handwrite it, and then you give it to somebody to type it. We didn't have a typewriter or anything to do it. So that was the level of thing. Some of my colleagues were using mainframe computers, but I did not. I mean, I was doing the very thing. So it is a very different type of research. Now, there's one thing that I would like to correct you. That is not true that today everything is on computers. I still do all my work by pencil and paper. So the principles have to be worked out, and these principles have to be. I mean, you can use some Mathematica or something to do some calculation, but the principles, the ideas, whether they work it out or not, or the main equations you want to solve, you do it in still pencil and paper. And most of my colleagues do the same thing. I mean, most of the colleagues who do in fundamental science do the same thing. Now, you mentioned your friend and so on. You might be doing either observation or phenomenological cosmology or observation connection or gravitational waves. And it's true that in both those cases, it is really a lot of work is coding and computers and so on and so forth. Because it is now the principles have been understood and they are being applied, and then the work is transferred to computer. So now I would say that maybe 25% or 30% of the work is the type that I do, and 70% of the work is more done in some ways on computers or on. It can be just on using some little program, or not the sophisticated programs like Mathematica, just to solve some equations. And it's not doing data analysis. Data analysis is a huge field, and that requires computational power, which is huge computational power. So how did this adaptive transition? It's basically the following: that the colleagues of mine who have remained, who have continued to think just in terms of principles, and they don't have to worry about this going on mainframe or doing numerical calculations or anything like that. Sometime in the 2000, so more than about 25 years ago, I would say, late 1990s, I decided that the the best place to test ideas, of course, of quantum gravity, the best home for that, if you like, was really the early universe, and therefore I needed to understand cosmology. And then one needed very much to understand how the data is actually taken, analyzed. And it was a steep learning curve for me because it's a different, altogether different thing. I mean, it's not sitting in a room and fundamental principles and so on and so forth, but much more about there's a lot of information, and how do you absorb this information? What is relevant, what is not, and so on. That you have to absorb. It's a different kind of thinking that is needed, and to me, it was a steep learning curve. And even to this day, I think when I have questions and so on, but I understand how things are done, but doesn't mean I can do them, in the sense that I don't go and do data analysis myself. But I realize that no, there's something not quite right about this idea, this particular conclusion people have written, or maybe one can improve this conclusion because of this factor. But then I have to ask my postdocs and students about actually to do this, to actually check that. And they are, of course, they grew up at a different era, so they are much more competent about actually using computers and using doing these calculations, or at least understanding the codes, even though they themselves may not do it, somebody else has done the code, and so on and so forth. So for me, it has been a kind of a transition in which I'm not, even today, I've not really gone to sitting there coding something. I don't do that. But on the other hand, I understand how things are done. And then with discovery of gravitational waves, this bridge between kind of theoretical research that I had done in the 1980s and 1990s with gravitational waves, that being transformed, or but that being connected, bridged to actual observations, is something that again needs a huge amount of computational power and so on and so forth. And I have to talk to people, and I do talk to people regularly who are good at that. And then there's a synergy. You need both these strengths, and there is synergy.
So when I talk about Chandra, so please tell us some more anecdotes about him, because I have been reading the stories of Chandra, Bose, Saha, Chandra's uncle, Sir C.V. Raman. So please tell us something more about it. Some anecdotes of with him that you would like to. There was a story that he was he used to do 10 years on one topic research, and then he moved to other field. He tried to do research on other topic, which was quite quite similar to what C.V. Raman sir used to do. I just had a little bit knowledge of Raman sir's life, because he used to do his research in different topics. Please tell us something about Sir Chandrashekhar, and what kind of personality he was.
Yeah, Chandra was very austere person. He was very pure. He got up, I don't know, 3 or 4 o'clock in the morning, and then he did his work. Then he took on his scientific integrity and what the role of scientist is, like a true sage. And it's I mean, at the celebration of his 100th birthday, 2010, in Chicago, to the conference, and I asked to make some remarks about Chandra and so on. At that time, I think I really said that. I'm trying to remember just a second. That Chandra was a true embodiment of what philosopher means in the strict sense of the word. And philosophy just comes from philosophy of failure. So there is love of knowledge. And Chandra really represented that love of knowledge, untarnished by things like fame, untarnished by things like, am I getting enough credit? And untarnished by saying, well, so and so is not really done that much work and just is getting more recognition and so on. So these things were, to him, there's really a certain amount of purity and a real amount of austerity about Chandra. That I think is kind of, everybody felt it from the word go, so to say. Then with his working style, as you said, is exactly right, that somehow you develop this habit of working on some area and really understanding it thoroughly and pushing it to an extreme, pushing it the frontiers as much as possible, really making a giant leap in that particular field. But then he felt that after 10 years, he did not have his contributions would be incremental. And therefore, he would rather not continue in the same area. That, it is always easier for most people just continue the same area because it's much easier, so to say, than starting from scratch. And also, starting from scratch means you have to make your name in a new field, which is always an upward slope. It's an uphill battle, so to say. But Chandra did that, and he took several months going into the library, looking at the journals in those days, Roger journals in the library, and seeing what is a good area. And then you would go into that area. Interestingly, however, for general relativity, he spent more than 25 years. Once he got into the area in the 60s, he spent more than 25 years. And that was the last area that he worked on. Yeah, you were asking something.
So he used to was he used to ask new people from the field to give him lectures on the topics, and were you the one of them who gave him the lecture?
Yeah, so I think, so I have to qualify, I mean, what make it more precise. So what happened is that when he decided to learn general relativity, what happened is that he actually went to a conference which took place in Warsaw to learn about general relativity, because he thought that might be an interesting topic. And it is at that conference that he heard various talks and so on. And then that made up his mind that this was a field that he wanted to do. And then he wanted to learn modern general relativity, because he's, as I said, his mathematics was really coming from the, late 1800s and early the very first part of the 20th century. And the general relativity mathematics that was used was a little bit more modern currently. So he invited these three young, bright people, very young people at that time, to come to Chicago for summer and lecture him. And these were three people. There was Brandon Carter, George Ellis, who was a cosmologist, written this monograph with Hawking and Ellis. Brandon Carter did a seminal work on black holes, and Robert Garrosh. And so these three people, Bob Garrosh, who then was my advisor several years later. So these three people came and gave lectures on various, forefront topics on general relativity. And Chandra, as a student, went to all those lectures and took detailed notes. And you would work through those notes, and you'd call them at night to get clarifications and to say that, well, you think this is a mistake here? Is that a mistake, or is it wrong, or whatever? He was like a genuine student. Here he was already, distinguished professor, so many honors and everything. And these were people, I think, at that 60s. So he was 50 years old at that time, and these were kind of kids who were in the mid 20s, late 20s, right? I mean, mid to late 20s or something. So they're 25 years younger than him, and so he had that, what I mentioned before, this sense of pure science, right? I mean, no distinction, no authority, no rank being pulled, and so on and so forth. So that is a very important story. Now, with me, it was not like that. He didn't learn directly things from me in the sense of, but he came to all the talks, even the informal ones that I gave, which I was always flattered by and a little bit, on the edge, because Chandra is in the audience, if you like. But I was a student, a graduate student. There's nothing. In particular, I remember two things. One is when Hawking discovered the famous Hawking effect, which is the evaporation of black holes. This was during my last year of PhD. And it turned out that in the group, I was the one who was best equipped to understand this discovery and what he was doing, because it was really in some ways continuation of the way that I was thinking about things. And so they asked me to give a talk on the Hawking effect. And Chandra actually came to that talk. It was really meant for other students and postdocs. And Chandra came to this talk. And similarly, At one stage, when Bob Garrosh and I were finishing this paper on quantum gravity, the particle physics paper, namely a famous physicist, Ichiro Nambu, he won the Nobel Prize also, just like Chandra. So Ichiro Nambu actually asked Bob Garrosh to have some talks on quantum gravity. So we decided to have 2 talks. But Bob was obviously the professor, I was a student. But Bob asked me to give the talk. And that also shows the spirit I was telling you before about this talk. And Bob was sitting there, and so I gave these talks, and Nambu came, and Chandra came, and all these people were always in the talk. And so I was very, very honored and flattered and also struck by awe, right? That these people at this age, at this stature, etc., are still willing to learn from younger people, which was very, very thrilling. Okay, I think we should move on. It's already about 15 minutes of interview, I think so.
Okay, sir. Okay, let's move forward. There is a lot of mention of asymptotic structure of space-time. So there is a great mention of that in your research. So please tell us something about what asymptotic structure of space-time means, and what is your research in that, so that people can understand about that.
Yeah, so basically, I mean, you know that in Newtonian theory, the force between 2 bodies falls like 1 upon r squared. So if I got a central body like the sun or a black hole sitting there, and I got some planet which is very far away, how is it going to move? Then Newtonian theory, it is going to be, the force is like 1 upon r squared. And so we need to know basically how to extract physics from the equations. And typically, to extract physics, you have to construct what is called as observables. So, for example, you may need to know what is the mass of a space of a given object, like it can be a star or a black hole or something. What is its angular momentum or its spin? How much spin does it have? Is it spinning, and how fast is it spinning? And so these are basic observables. Now, to extract this information, it turns out you really need to go to far away. And far away, the structure of the curvature of space and time simplifies, because near the object, space-time can be very curved, and it is difficult to meaningfully extract the value of the mass and the momentum or the spin, and it can have multiple moments, like so-called quadruple moment, how distorted it is, and so on. From near the object, it is very difficult to distort this, to obtain this. Also, how much energy is radiated, for example, by electromagnetic waves or gravitational waves. How much energy do they carry away? What happens? So this is difficult to know when you are, so to say, near the object. You have to be in a very far zone. And this analysis of the fields in a far zone is called asymptotic. Asymptotic just means far away. So you are going far away, and there the curvature is weak. So space and time look like flat space and time. They're like more familiar space and time, and you can extract the quantities that are of direct physical interest by going there. But it turns out that in general relativity, so this is what we do even in electricity and magnetism. To calculate the charge, it is true that charge is you can make an integral on a 2-dimensional sphere of the electric field flux, and that integral is the charge that is contained in that particular region. And so we could do a similar thing for a mass or something like that. But in general relativity, the problem is that what you mean by 1 upon r, like a 1 upon distance, if you like, 1 upon r is 1 upon distance from the body, itself depends on the gravitational field. But the gravitational field is not flat. So gravitational field is curved, which is determined by the body. So you're trying to find the property of a body which determines the gravitational field, but the distance, notion of distance, is determined by this gravitational field itself. So it becomes a very kind of convoluted circular problem, right? Because what I have to go far away, far distance d or r, far away. But how do I know what r is? Because I got this curved geometry. It's not just x squared plus y squared plus z squared. It is something much more complicated. And so that disentangling of what you mean by, in precise way, how much far you are gone, 1 upon d, 1 upon distance square, and so on and so forth, from the curved geometry makes this problem quite complicated in general relativity.